Hello and welcome to a special episode of the Trash Talk Podcast. I'm your host, with the day of Sergej.
Hello.
Today is a very special episode because it's a nice round number. It's 256. And since... Should I explain why it's a nice round number and why we chose the topics, or am I just going to go with it? Okay.
No.
Today, we're being very logical. No one can accuse us today of being illogical because we're doing logic. This is NandGame. So, we're not covering anything essential.
Okay, the thing I just realized is my camera probably covers up, or might cover up some important stuff.
So, right now it works perfectly. It's not cutting off anything of the logic table on the left, and it's not cutting off anything here except for, like, the trash can, which doesn't really matter. I mean, it would have been good for branding, but,
Yes, obviously.
NandGame is all about NAND, and first of all, we're gonna build a NAND gate. Now, what is a NAND gate? I think is the first question. So for those that don't know, right, we're dealing here with Boolean algebra, or binary logic. That is how your computer functions. And so we're gonna use ones and zeros to get ones and zeros. We have our inputs at the bottom, and our output at the top, and we have to make sure that our inputs produce the correct outputs by adding gates, or in this case, relays. Normally the gates, these are relays, they're kind of like gates, they're technically gates. It doesn't matter. And so, every gate has a certain function based on its input, it gives a certain output, and we are supposed to basically make, by wiring them up, the certain output happen. Now,
yes.
A NAND gate, specifically, you can imagine... So, let me start with AND and OR gates. I think that's the easiest place to start. An AND gate outputs 1 only then when both inputs are also 1. A OR gate outputs 1 if at least one of the inputs is 1. And if you then add the letter N in front of their names, you get NAND and NOR gates, which do the exact opposite. So, a NAND gate always outputs 1 unless both outputs are 1. And the NOR gate outputs 1 unless at least one of the outputs is 1, which is to say, it outputs 1 when both inputs are 0.
Mm-hmm.
And right now, we have these relays, which are more complicated in a way than the NAND gate itself, to try to build a NAND gate. So our goal, and you can see the table on the left here, ever so barely, is to make it so that when A and B are 1, the output is 0, and all the other times it's 1. The way these relays work is, this is actually the reversed one. This is the regular relay. When there's a current on C's control, it connects from in, which is input, to output. So, basically, it just passes through the signal that you get here. So we have our two inputs, and this is, by the way, is just a 1. Right? So if we want something to always be 1, we put it here. Now, if I were to connect this to the output, it would not produce a 1 here, it would produce a 0, because there's nothing, it's closed, right? It doesn't let the signal through. Now, if I were to connect this to one of these, and then set it to be 1, then it lets it through. If it's 0, it doesn't let it through.
I forgot you could toggle them.
Yes.
It's been a while.
And so the way this works is, right, so I explained that, and then this one works the other way around. So if you have a 1 going in, and let's connect it to this one, then it's going to let it through unless it has a 1 going into it. So if I toggle this, now it's 0, and now it's 1. So the default output is always 0, and then if control is on, then the output is whatever input is. So, I'm going to clear the canvas again. And now we're going to demonstrate how to actually build a NAND gate. So the first couple ones we just know how to do. NAND gate we figured out yesterday before we started recording because honestly the relays were new to us. And the other ones we kind of know already because they're relatively basic. I studied computer science in college. I did stuff like this before.
Yeah, same.
So, the the easiest way to build an AND gate, which is also the intended way, so the goal is generally to do with a minimum amount of components. And that actually, there's a reason they give us two types of these, uses both of them. Now, it is interesting to note that the default off one, I always get this mixed up. I think I want this one. The default off one, is basically
behaves an AND gate.
Yeah, it behaves identically to an AND gate. So, because if the input is 0, it doesn't matter what the control is, right? It's always going to output 0, because even if the control pushes the input through, it's still going to be 0, right? So if it's off, or if it's pushing 0 through, it's the same result. And so if control is 0, the output is obviously going to be 0, so only if both are 1 does it output a 1. So this is an AND gate, which is the exact opposite of what we want, as it will tell us here, right? So what we want is to... I don't think I can actually disconnect the connection, but it's fine, because
you can drag it to some empty place.
Oh, can I? Oh yeah, good, cool.
Yeah.
And then what we found out as well, this one can be set up to function like a NOT gate, which is to say it inverts the input. So the way that happens is we set the input, we set the input to be 1, and then we set the control to be this output. Now, what this does is that means that it outputs 1 unless the control is 1, in which case it outputs 0. So it outputs the exact opposite of what control is. So if we wire this up, ta-da!
Pass a test.
Now, I think we want to demonstrate something else, right?
Oh yeah.
So okay, what is it that we said about... So we said that the default off is basically an AND gate. What did you say the default on was?
It's an AND gate with one of the inputs inverted.
And we already said...
The input being inverted is C.
Yes. And we already said that the default on can be used as an inverter. We literally just did it. So what we're saying is we use this as an inverter. So if we want to use it as an inverter, we hook up in to the power and C to whatever we want to invert. And then we can use the same default on and hook up C to the now inverted output and hit in to the other output. And now this whole contraption, which I should have wired up the other way around for simplicity's sake. As a matter of fact, let me... Wait, yeah, I mean, it doesn't... Yeah, it doesn't really matter. I should have wired A to the bottom and then B to the... I could have aligned them better, but it doesn't matter. I just don't like it that they're crossing on the diagram, but it's fine, it works.
That doesn't really matter. I think it's unavoidable.
Out of 2 relays, we build an AND gate, and then with the third relay, we can use it as an inverter, again, with this output of what is effectively now the AND gate, and then connect this to the output, and now we use 3 gates, but we only use one type of gate. In other words, it was completely unnecessary to give us the default off.
Yes, but it is more complicated, so...
Next level. This is when we get our NAND gate. This is what we just built. And this actually is arguably trivial. Is asking us to build an inverter, or a NOT gate as we would call it, and the signal should be the opposite of the input. So if we... A NAND gate outputs 0 if both inputs are 1, and 1 if both inputs are 0, and the other 2 cases don't matter because we only have one input, so we just hook the input up. Ta-da! Build AND gate using only NAND and inverters. Do you want to explain it, or should I?
Easy stuff. I mean, since a NAND gate is basically an AND gate with the output inverted, we just have to invert the output again to get the actual And
I'm going to do it the way Sergej likes to do
which
it.
we can do either with... Yes.
Obviously, we just demonstrated how we can build an inverter using a single AND gate, a single NAND gate. So we might as well not use the inverter that we now have access to, because this is the exact same thing.
Yeah.
Which actually technically means
Just
we never
takes
use inverters.
more effort.
I mean, yeah, we're probably going to actually use inverters in the future, because it just is one click fewer to connect them. So it is faster. But we're not speedrunning this. Which means it's fine. So, an OR gate. Should I explain De Morgan's rule?
Yeah. I guess.
I think that actually is the easiest way to build it anyway.
I think it might be important.
So De Morgan's rule says that if you invert the inputs, okay, so if you have an entire formula that says A and B, and then you negate the entire thing, then you get not A or not B as an output, and inversely, if you have A or B, and you invert that as a whole, you get not A and not B. Meaning, if you invert the inputs of the equation, you basically get the opposite. So, if you invert the inputs of an AND, it's an OR, and if you invert the inputs of an AND, it's a NOR. Basically. Did I explain that sufficiently?
I think so.
I mean,
honestly, it's kind of tough for me to follow the this rule, the explanation of this rule, if it's in circuits. I find it much more intuitive in programming when I do if statements.
Yeah, there's also a way to write it. I don't think I have it. I'm not sure if I probably have it somewhere in my notes, but I don't think I could find it right away, because there is a good way to write it, but then again, I would have to explain to you Boolean algebra notation anyways, because otherwise I don't think it's going to mean all that much for you, as in the viewer. I'm sure Sergej knows it, but I briefly showed off the circuits before, and you can see how this kind of goes nuts when you start actually looking into it, right? Like, there's a bunch of lines above equations, and those are negations.
If you invert it twice, the whole thing?
It sure looks like it. I don't remember why. I'm sure there's a reason for this. It might be partially related to the fact that... Nah, it doesn't matter. But yeah, you use pluses to mean OR, and you use the dots like in multiplication to mean...
Multiplication.
Or sometimes you just write them together as well. Doesn't really matter. This is an OR gate. And I'm fairly certain that this is the easiest way to do it. 3 components used, 3 NAND gates in total. This is optimal.
That's good.
And my favorite, the exclusive OR. It outputs 1 when exactly one of the inputs is 1. So if both are 1, we get 0. If both are 0, we get 0. If exactly one of them is 1, we get 1. This is the first one that
Good stuff.
That I can't do without having to think about it for a second, because I genuinely don't fully remember. So it is, if I do a regular OR, we get everything right except for this last bit. Which means if it's OR and not AND, is that what it is?
Yes, that is correct.
See, I told you I just had to think it through. I just didn't remember how it worked.
Mm-hmm.
But it is relatively intuitive. So, to explain, right? The OR outputs exactly what we want except for that last condition. Right? Like, this last line doesn't work. The NAND outputs 1 only if... Wait. NAND outputs 1 only...
No.
In those first three cases.
And NAND outputs 0. Yes.
And so...
That's correct.
In the first 3 cases, we get the NAND to output 1. And in the last 3 cases, we get the OR to output 1. And the AND only outputs 1 if both the NAND and the OR output 1, which is the overlap here in the middle too.
Yeah.
Next level. a half adder.
Oh, it's possible to solve it with a lower total. Interesting.
Oh, I think it might be because I think this is the fewest possible components, but it's solving with fewer NANDs as possible. Probably because and OR gates are because OR gates are relatively complicated. In terms of number of NANDs.
Probably.
So do we want to try to figure out how to do it with fewer NANDs, or do we just accept it?
I don't think so. Nah. We'll just accept it.
I'm pretty sure this is how you would build it. I think it's literally how we learned in college. Like, this is how you would build it. It's also the most intuitive way to do it. An add component.
Yes.
Now we have two outputs. That's the first time that happened. The output H is the high bit and the L is the low bit. It's a complicated way of saying that this HL is a 2-digit number in binary. So we get two inputs, which are 1 or 0, and then we have to output the result, which is either 0 if both are 0, 1 as in 0, 1 if exactly one of them is 1, and 1, 0 if both of them are 1.
Yeah.
Which actually makes me think that this H is basically an AND the L is basically an exclusive OR.
I mean, that would make a lot of sense, yes.
The problem is because I'm controlling the mouse.
Just purely looking at the... Yeah. It is kind of dubious because I cannot really interact with the thing.
Yeah. I mean, I don't think there's a good way to do that because I'm controlling the mouse and I'm already the more dominant talker here. It's just a lot of me just explaining how it works.
Yeah. I mean, we could probably theoretically set up some kind of TeamViewer thingy, but that's also kind of dubious.
Oh, yeah, no. I mean, honestly, it's just, if you want to walk through one of the problems, you just have to say it, preferably before I start talking, which I get is difficult.
I mean, anyway, it would be kind of hard to do if I'm not in control of the mouse.
Yeah. I mean, you just have to tell me what inputs go together. I mean, I explained it pretty easily, right? Like H is an AND and L is an OR, XOR, and then... I mean, I know the way I said it doesn't technically make sense, but I feel like it's intuitive to understand what I meant. By the way, for those wondering...
It makes sense to me.
The way I wired up A to A and B to B is arbitrary, and it just makes it cross over fewer times, so it actually looks more palatable, but it technically doesn't matter. So could I do something?
Yeah.
It just looks worse. Actually,
it doesn't.
That is...
Yeah, no.
Simplify that much, but... I mean, I could if I wanted to wire it up like this, and it would... Nope. There we go. And it would still work. It just looks worse. I was just bringing that up because in this case, for the basic logic gates, and as a matter of fact for the adder as well, the order of the inputs does not matter. I just want to make that very clear.
Yes.
It actually does for one of the relays, for the default on relay. It's the only one where the order of the inputs actually matters.
Oh yeah, yep.
Fewest possible components. We can use fewer NANDs. I'm not 100% sure how it calculates the number of gates we use though, because it already said our XOR is suboptimal, which might just be the reason why this is suboptimal as well. If it does keep the gate count that we previously used. If it assumes optimal XOR, then...
I don't know if it does.
There would have been... I don't know either. That's what I'm saying, right? I genuinely don't know. So next level is called a full adder. So this
we can probably, if we build it out of the actual components of XOR, we could probably just reroute one of the intermediate values to H. I think this is what they're talking about.
Oh, because... No, but it uses a NAND. So, right, so instead of using an AND, we could use a NOT, which would simplify it. You know what, let's do that. Let's stay at this level. Let's clear the canvas. Yes, I will.
That is...
No, that was the levels.
Not...
I
what?
clicked the wrong This
Wait,
one.
can we jump back to the one? Did it lock it?
I think there's a skip level option. I think we could have done that. Yes. Which I guess we should.
Oh yeah. Yeah. Just skip the level.
Half adder.
There we go.
This is what we wanted. I'm sorry, that was my bad. I clearly should have paid attention to the fact that there was not previously a message when I hit clear, and then now there is. So that was on me. So if we actually build the XOR, which is to say that we use a NAND and an OR.
Yep. I mean, the solution wasn't really optimal either, but still. It's probably more optimal than what we did previously.
In a real computer, the amount of components that you use doesn't matter because it's just the amount of NAND gates, because your actual processor is actually most likely made up of NAND gates. I think sometimes they're made up of NOR gates, I think. But yeah,
probably.
That is the thing. So now this, obviously, if we put it with AND, gives us exclusive OR, which is what we said we wanted for the last component. And then if we use an inverter, as they call it here, outputting it from the NAND, that gives us the AND that we wanted. 4 components used. Yep. Mission OR is not completed, so the total number of gates could not be counted.
Oh, okay, so it does keep track of the ones we used.
Which also means that because I deleted our previous levels, we're never going to have an accurate count, which is actually kind of annoying. But we would have been suboptimal anyways because we haven't gotten the optimal XOR, so you know what? Fuck it. So, full adder. The reason why the other one is called a half adder is because it doesn't have this C. Now, this C is not just a third number. Well, I mean, it is. But it is also the carry from the previous calculation. So that's why it is sometimes...
Yeah.
That is why it's generally referred to as C. In this particular case, it doesn't really matter, but...
It just happens to be ABC as inputs.
Yes. So the reason why you want that, of course, is if you have an adder, and you add your A's and B's together, and then you want to calculate a number that has more than one digit. So if you want to add like 1 0 and 0 1 together, well, obviously it's 1 1, that's intuitive for you, but then you want to add this 2-digit number. No, you want to add the back digits first. The rightmost digit, what we call the least value digit, I think, something like that. Lowest.
Something like that.
Least valuable digit, I think that's what it was. Least valuable bit, obviously. So that one, you add those together first, and then you have L as a new least valuable digit, and you have H as what would then be the C in the next step, the carry. And then you add the next two digits.
In this case, you can also just treat every input as a single 1-bit number. So it doesn't really matter in which order we add them. But if you have more bits per input, then yes, that does indeed matter.
So, to do this, we want to add all 3 numbers together. So this adds 2 of them together. And then this adds the other 2? Oh no, wait, so this adds the third number to the back. So this is our carry in the literal sense.
I'm not sure where you're going with this. Wouldn't you want to add the high bit to the second adder?
I was thinking no, because if you have 0, 1, 1, right? 0, 1, 1.
Yeah.
Then you get, this will output 0, 1, and this will be a 1, right? And if you add the 1 to the 0 in the beginning, that'll give you a 1. Which I don't know what you want to do with that, right? But if you add it to the 1 back here, it'll give you a 1, and it will give you 1, 0.
Okay. Continue, please. Then.
I mean, I still haven't fully figured this out. I'm like working this through as I'm talking, but
Okay. Yeah.
the idea is if you have a 10 and you add a 1 to the 1 in the front, it doesn't really make sense, right?
Mm.
I mean, if you have 1 0, then you add 1, and then you should have 1 1. So because we only have 2 digits to output, so this lowest digit is the actual lowest digit. And then I think we add the higher digits together again. That doesn't make sense, though. Wait, now... Oh, no. I think this one is trash. If this outputted 1, then this one can't output 1. So only one of them can output 1 at 1, so I think I can just connect them with an OR gate. Hey, I did a thing!
Okay.
So, if you're thinking about adding 2 numbers together, right? Multi-digit numbers, then you always have to add... Oh, I see how he came up with adding to the first one. Yeah, that makes sense. But you have to consider, right? Like, you add 3 numbers together. So they all on the same digit.
Mm-hmm.
But the adder only has 2 inputs.
Yeah.
So we're adding the last digit of this one over here, right? So I think the easiest way to imagine this is literally to just say it is 1 0 1 or something. And so, right, if it's 1 0 or 0 1, it doesn't matter. But if the first 2 outputs in this case, I could have, of course, mirrored the entire construction. If this together gives you 1, then adding a 1 to the 0 doesn't make sense, in my opinion, right? But adding a 1 to this 1 at the back does make sense.
Yeah, I see. That does make sense.
So, and then the high digit, if this is a 1, the high digit will just be a 1 no matter what this in the back is, and then this basically just passes through the last digit.
Mm-hmm.
The problem is I don't know how to explain this any better, but it makes sense to me, and it is correct, which is a good combination.
Yeah. This is the simplest possible solution, by the way. That's good.
I think we're gonna do a multi-bit adder, and then we're gonna go to the halftime show, and then we're gonna go to the rest of these. We're probably not gonna do all of them, but...
Oh yeah, no, it's way too many to do all of them.
Now build an adder that adds 2 2-bit numbers and 1-bit carry. 2-bit adders can be repeated to make adders that make larger numbers, but that's the case for 1-bit adders as well, isn't it?
Not quite, because with 1-bit adders, you all 3 inputs are treated as single-bit numbers that you just add together.
Fair.
With 2-bit numbers, you actually have to think about the order of stuff.
So... I mean, I'm just doing it right now, but I think this is correct, right? You have the lowest bits and the carry
I think so,
add
yes.
together, and then the highest digit here will be treated as a carry this time around. I think that's what you were thinking about earlier, maybe. And the higher digits plus the carry from the last digit will be added together, and then this gives us a 2-digit number. Which actually is a problem, because I need 3 outputs. Oh,
no, we have 3 outputs.
Is the lowest digit, right. So
we do have 3 outputs.
This is the carry.
I think they're in the correct order. Yeah.
This is the back digit.
That should be it.
So that's what I was saying, right? Like, you can add 2 1-bit adders together to make a 2-bit adder. As you can chain 2-bit adders.
Yep.
It's the same logic, it's just...
Yeah.
So what we're doing, for those that haven't quite understood this yet, because I know that this is probably a lot if you haven't dealt with Boolean logic at all. I'm not sure if you can even follow this far. But what we're doing is we're adding the last digits plus the previous carry together to make our 1-bit adder, basically. And then we're treating the higher number there as the carry for this next operation, together with the 2 higher digits. And then the new carry is the higher output of that, while the higher digit is the low of this, and the low digit is the low of that. I still didn't explain it very well.
I think you just confuse more people than
Yeah, so
you
the
helped.
thing is, right, what we're doing is we're showing off that we can do this while trying to explain it, but not doing a good job at that. That's what this is.
Mm-hmm.
So yeah, this is... Oh, we have a 16-bit adder. So this we're getting into big time stuff. Add 1 to a 16-bit number. We're doing that later. For now, we're doing halftime show.
Oh god, the compression.
No, we're not doing halftime show at all.
It's struggling.
Doesn't matter because no one will see that. And your compression is fine.
Yeah.
Which is all that matters.
Okay, that's good.
Facts of the week. Before we do halftime.
Okay, let me pull up my fact of the week. So, have you heard of this good guy named Jean Boulet? I think is how you pronounce that name.
Sounds possibly vaguely familiar, but I think it's also just a relatively generic name.
Probably not. He was a helicopter pilot, and he set a couple world records with helicopters. One being when he flew a modified helicopter to an altitude of 12,442 meters. That is a very high altitude. It roughly translates to 40.8 thousand feet. So, and problem is, at this high altitude, there is very low temperatures and very low air pressure, which helicopters don't really like that much, or engines in general, I think. So, at that high altitude, his engine just went out.
Okay, that's
which
not good.
Is kind of a problem. And the bigger problem with that is, to even reach these high altitudes, he and his engine crew or whatever, modified the helicopter to remove pretty much any excess weight they possibly could, including the battery. So you couldn't restart the engine.
That sounds very bad.
Yeah. But the good thing is, helicopters can be powered through just the air moving through the blades.
That makes sense, yes.
You can't start up the engine with that, but you can land with that amount of force generated. And so he did. From 12 kilometers up in the sky, which earned him a second world record for the longest unpowered helicopter flight.
Yeah, sure. I mean, sounds like a fault to me, but yeah.
Yeah. Which, the thing is, there was a condition for the first world record of the highest elevation, which was that he had to land within a certain perimeter of his starting point. Which is really hard to do if you don't have power in your helicopter and no navigation systems, because you remove them for sake of losing weight.
Yeah.
But he did manage it, nonetheless.
Okay, that's kind of cool.
Which is amazing.
You know what I immediately had to think of when you started talking about elevation and well, him falling down and all that stuff.
Mm-hmm.
Have you heard of Felix Baumgartner?
Don't think so.
He apparently held the record for skydiving, exit altitude, vertical freefall distance, and without a drogue parachute, and vertical speed without a drogue, which I don't know what the drogue is actually, come to think of it. A drogue parachute is a parachute designed for deployment from a rapidly moving object. It can be used for, okay. So I guess it's just without a parachute. By jumping an estimated 39 kilometers. So he jumped out of a helium balloon.
39 kilometers?
From the stratosphere. 39 kilometers down. Yep. I'm pretty sure I saw it live on TV as well. Because that was a big deal when that was happening. And apparently, with a parachute, it has been beaten by Alan Eustace. I have no idea how to pronounce that. Who jumped from about 41.42 kilometers. So yeah, that is a thing that happened. Also, by the way, about Baumgartner, he reached an estimated top speed of 1,357.64 kilometers per hour, or Mach 1.25, which makes him the first person to break the sound barrier relative to the surface without vehicular power on his descent.
Nice. Man, people are crazy.
And that's not my fact of the week. I just thought of that when you mentioned the whole helicopter guy. My fact of the week, see, it's a special episode, you're getting a bonus fact, is actually about something that I had heard of before, and I wanted to use it. I think I thought at the time that I might want to use it as a fact of the week, but then I forgot, and then I found it again, by chance. So, this is about how wolves actually make the road safer. Because of course they do. A study in Wisconsin showed that wolves scare deer and reduce the automobile collisions by 24%. Because...
that is a lot.
Wolves prey on deer, and obviously, and that makes the deer scared, and when there are wolves nearby, deer, where does it say the exact line? Scare deer away from linear landscape features, including roads. Because apparently that's where wolves tend to prowl. Now, the wolves apparently, as far as I know, don't get hit as much by cars. But the deer just avoid roads because they're straight, more or less. Or linear, I suppose, which I don't know if that's about height or about... But yeah, no. So, yeah, deer tend to avoid roads if they have wolves nearby.
That's fascinating.
Yep. So, the way I first learned this, actually, because I heard it on a quiz show. Because they were actually asking, like, hey, why, what did they find out could reduce collisions or something? And then it's like, yeah, wolves. But yeah, so this is... I found an article about it as well. So, that is that. Now, for a second computer-themed game quiz type thing, we're doing a crossword.
Kind of computer.
And we're not just doing any crossword. We're doing a crossword based on the Adobe Password League. So, I have played around with this one before, so we're doing the next one. So these are somewhere between 101 and 200, as in the most common passwords, on Adobe, as per the leak. Though technically the leak didn't leak the passwords, it just leaked the hints and the hashes. But we are now trying to figure out what these things are. So, food, mouse, dairy, cheddar,
Mickey,
yellow,
probably.
fromage, Swiss, yum, fair food, queso, yummy, food, smelly, usual, mice, cheesy, mouse, food. I mean, it's cheese, right? Like,
Yeah.
Oh
yeah, we
and I
have
just
to
realized this
click
is
check.
I'm an idiot actually because this was actually the 6 across hint, not the 1 down hint. So let's try that again. Nope, that was not an H. Okay, I don't like, by the way, how this handles. Because oh no, you can use the arrow keys to go back. It actually isn't that bad.
Okay. Also, 1 down is actually probably Mickey then.
Mouse, dog. Oh, they're both. Mouse, dog, Disney, cat, pet, nickname, name, mouse, cartoon, Disney character, blah blah. I guess it would be. I'm confused because there's a lot of dogs in there, but I guess people name their dogs Mickey, which, to be fair, whatever. By the way, we could hit check at any time to check if what we have entered is correct, but I low-key want to try to see if we can do it without checking at all.
Oh, okay, yeah, that makes sense.
Q down, keyboard, QWERTY, so it's just QWERTYUIO. So, by the way, something that you'll notice is that the solution is never in the hints. I don't think they allow that.
Mm-hmm.
Wait. Huh. So obviously, sometimes you have the start of the answer. This keyboard is in here.
Yeah.
Q3.
Is it maybe QWERTY 1 to 3?
Q1 to 3. Was it QWERTY 1 to 3, actually?
Probably.
I see. Because it would have made more sense to me, until I saw the fact that there's a lot of numbers in there as well. Yeah, It would have made more sense to me. I love for this one just as password as a hint, which is very common, which is kind of funny, because it does actually not tell you anything about the password, because the password actually isn't password for once. Also,
or the bottom left one, which has a space between QWERTY and 1 to 3.
What?
Bottom left one in the list.
Yeah. As long as there's one character off from what your actual password is, it doesn't matter. I also like how there's tastiera, which I assume means keyboard in Italian, and clavier, which means keyboard in French, are on there as well. So very international on that one.
Yeah.
I don't know what Bebo means, and I don't know why this one says hi and this one says name. Those seem relatively bad. Unless I guess your username is also QWERTY123. Anyways, I guess let's do. Let's do the ones that we already have at least one thing for. 1, 2, 3, 4, 5, 6. Okay. It says A. Is it A 1, 2, 3, 4, 5, 6? I mean, the first two hints are literally A and 1, 2, 3, 4, 5, 6. Then again, one of the hints is triple A. No, I'm pretty sure it is that, because this is backwards, and this is everything but the 6. What is a question mark, though?
No clue.
Question mark. This one says QQ. This one says the usual, which I've seen a couple times come up as password hints in the other one as well. So that just tells you that that person doesn't just use a very bad password, but they use it everywhere. Which is great. Mm-hmm. This person said Adobe, presumably because their password is always the first letter of the service that they're using, and then the numbers 1 through 6. I don't know. That's just a guess on my part.
Good stuff.
Numbers.
I guess this would be a good place to plug the usage of password managers.
Oh, yeah.
Seriously, people use password managers? Also, so easy.
Also, apparently,
it protects you from so many different attacks.
Yeah. Números. I guess that is, if I'm not mistaken, that's Spanish. I was gonna say that Spanish speakers apparently use a password more than English speakers, but I realized the thing. There are more native Spanish speakers than there are native English speakers. So, That actually does check out.
Yeah.
Sequence. Numeral. Nome?
It's weird that they have
Is
the
it
10
Italian?
in there.
Or is it Latin? Nombre. What did you say?
It's kind of weird that they do actually have the 10 in there instead of just the 0.
Yes. But it does say 1 through 10, so I'm gonna assume that he's correct.
Yeah.
Count 110. Oh! Yeah, the pound symbol. That also means number. Which is interesting because I use it sometimes in our video titles for the podcast, for example. It'll say like, pound symbol 256. But YouTube interprets that as a hashtag, which means that you can actually click on it and it'll take you to YouTube search of just hashtag 256. Which I get what the feature is about.
Kind of interesting or dumb that you can't disable that.
I mean, maybe you can escape it. I'm not 100% sure. But also, like, I would by default assume that if it's just a number, then it maybe it's not intended to be a hashtag, but a number. And it's not just on new titles, but it also retroactively added it to all the previous podcasts. Which is the main reason why I kept doing it. Because otherwise I might have just considered changing it up, but no, I don't know. Let's see, what else do we have hints for? How about the 7 down? Numbers! Oh yeah, right, obviously. Honestly, this one is less interesting than the first one, because...
I think it's just 1, 2, 3, 4, 5, 6, A.
Is it A? Oh yeah, it is A. The weird thing is that this one is actually easier, I find, than the first one. Now, granted, I now know how it works.
Yeah.
But, like, one of the passwords the first one had was shadow. And, like, some of the top hints were, like, cat. And I'm like, huh? Because people apparently named the cat Shadow, which I guess makes sense, right? And then, because it's your cat, the cat would immediately make you think of it. But that actually is a lot harder for me than just a bunch of numbers, right? Let's do 10 across before we forget it. Email, MSN, mail, hot, email address. Regular.
I think it's just Hotmail.
I guess so, yeah. It's just their internet, their mail provider, yeah. Okay, this is 1, 2, 3, 4, 1Q. Oh, is it 1, 2, 3, 4 QWERTY? Or is it just QWERT or something, right? It does say QWERTY in here, though. I think it's this. I think it's just 1, 2, 3, 4 QWER or something. 1, 2, 3, 4 QWER. Because it couldn't actually be QWERTY.
Yeah.
Because right here it says wie immer, which means as always in German. And that's actually why I found Klavier to be interesting in one of the other QWERTY ones, because I didn't know that France used QWERTY, right? But Germany uses QWERTs, right? So we have a Z with a Y in the English keyboard, which means there wouldn't be a German hint if it says QWERTY in the answer. At least not in like the top 20 hints or whatever it is that is in there. It's probably more. But it probably just wouldn't be in there. So, yeah. That is that thing. Numbers 0 through 9 numbers.
This is just boring.
I know, right? I was expecting this to be more fun. Password. Password 1. Okay, great. Is it capitalized? It doesn't say it's capitalized, right? Some of them do capitalize it, though. Okay. Wait, do we reckon this is capitalized?
Now that you mention it, yeah.
Because this is capitalized.
Yeah.
This is capitalized.
There are a lot of capitalized ones. Yeah.
Because I assume that this quiz is case sensitive because your real password, I would hope, is...
Yeah.
I mean, I don't know. Their security practices are pretty bad. So for all I know, it's not, but... I think the main problem was that they weren't salting their hashes, right? That was the main problem. So you could collate all of the hints to the hashes, and thereby...
Yep.
Car, auto, carro, red. So it's Ferrari? Is that what it is? F1, favorite car. Cars, car, voiture? F1, Enzo, auto, fast car. Oh, it's auto, right? It's actually German because it's capitalized. I swear to God, right? Like, There's a lot of Germans using this as a password. Well, Scuderia, I guess it's maybe Italians as well. F. Schumi, as in Michael Schumacher, who famously drove for Ferrari. I'm not. Why did I say it with a German accent? Like, if anything, I would have had to say it with an Italian accent because it's an Italian brand. It's. I don't know who Enzo is, but it's definitely Ferrari, which is spelled with how many R's where?
I think 2 and then 1.
Ferr.
If I am not mistaken.
Yeah, I mean, that's Spacewise would make sense. And I think it's time to check, huh?
Yeah. It's all correct. I guess that would be time to check if it is case sensitive or not.
I mean, yeah, I'm pretty sure it is, though. It will be a big oversight on the quiz if it isn't.
Yeah.
Yeah, it is.
It actually is.
I mean, I guess good on those people for actually using a capital in their password for once. I think this is the first time I encountered a capital letter, including the first quiz. So, like, yeah.
I mean, look at that. They have a capital letter, they have a lowercase letter, and a number. They were doing much better than, like, everyone else in this quiz.
And I mean, to be fair, it's also like
it's still
1,
really
3,
bad,
4,
but
5,
still.
6, 7, 8, 9 characters long, which also makes it one of the longer passwords in here. Like, as far as best
not
practice,
even brute forceable.
Like, as far as best practices go, they're doing surprisingly well. Oh yeah, I had it the next time over. I wouldn't have had to even. But yeah, no, that was. First of all, it wasn't as interesting as I would have hoped. So that's on us. Sorry.
Yeah.
But yeah. So we're incrementing by 1. Oh, we have this.
Because we definitely need that. They couldn't have just added the
1 at the bottom like they did last time.
1. Yeah.
So.
But fair enough.
Wait, this is a 16-bit number? Is that it? I mean, I know I didn't explain anything. Okay, so first of all, it says in a very small font, it says 16 right here, and on this S output.
Oh yeah, actually, I can't actually tell.
So it actually is 16 bits, and so I'm adding a 1 via the carry because I don't think I can add a singular 1 to this. And if I can, this might actually end up being 1 on every bit. I'm not perhaps not sure how that works, so I'd rather not. So I'm adding 1 as the carry, and the previous number. If we bitwise add zeros to it, it doesn't change anything. And then the 1 in the carry should increment this by 1. I think I'm doing this correctly, aren't I? Okay.
Am
I doing this
correctly? I think so, yeah.
The other thing that
I wouldn't know.
Weirds out a little bit is that we're using 16-bit numbers, because I think by default an int in program would be 32 bits, I think, and a lot of times it would make sense to have this be byte-wise, as in 8-bit. So 16-bit seems like a weird compromise. Like, I think this is the length of a short in C++, but that is still a bit odd to me. Yay, we did a thing.
Woo!
2 components used, not counting 0, which does not contain any logic.
Fair enough.
Build command that subtracts 1 bit. Subtracts 1 bit. So okay, do we just want to do 16 increments? Is that what we want to do? Not 16, obviously. 15 increments? And, it wouldn't have to be 50, it would have to increment every bit, right? Well, if we subtract 1, right, we could just, so it wouldn't be 15, it would be like 255, right? Is it? No, it's not to the 16 at all. But like, 2 to the 16 minus 1, we just, okay, hear me out, right? We just increment it often enough to get an overflow. Wait, subtraction. Oh no, it's not subtracting 1, it's subtracting numbers. Never mind. Oh, I see. Yeah, no, we're subtracting numbers. So we're subtracting a minus b. I thought this was subtract 1 for some reason, like a decrement, but it's not. It's actually subtracting numbers. So we have a new component called the inverter 16, which is going to be important. We have an adder for 16, which technically didn't need to be a full adder, but... and we have an increment. I think that's all we need, actually. Okay. So we definitely need to make use of the overflow, right? To make a subtraction. Like that is, I think, genuinely something we have to do.
Yeah.
I think it's something like you add the inverse of the number and then increment it by 1 or something like that. I think it's somewhere around there. I just have to remember exactly how this works.
And just try it. You have all the components on there.
Let's see, if you had a 1 and you wanted to... If you have something that says 1, like literally like decimal 1, right? And you want to subtract decimal 1 from that, then...
Yep.
Then you would want to add everything but 1 and then 1. And then, no, you're back to 1 then. You want to... No, that's correct, right? If you add inverted 1, which is 1 on every bit except for the last, so it's like decimal 2 to the 16 minus 2, then you get 2 to the 16 minus 1, which is the maximum number, and if you add 1, it flips over with the overflow and it becomes all zeros, which is exactly what you want. So for 1 and 1, it works.
Okay.
The logic that I had, where you add the inverse of the second number. Now, what if we wanted to subtract 1 from, let's say, 2 to the 15 minus 1? As in 0, 1, 1, 1, 1, we want to subtract 1 from that. Now, if we add 1 and a bunch of 1s to it, it has a bunch of overflow, so it should shift over to being a bunch of 1s. And then, because we invert the 1, not a 1 in the end. But I'm not sure if that works. You know what?
I don't think I can follow your explanation, but just try it, I guess. Didn't connect. Yep.
And technically I want to increment this output, but what I also could do is I could also add a 0 to the carry, which is the same thing as incrementing it, which makes this increment just... I mean, I guess complication-wise it doesn't really change. No, it does add a lot of complication because we're adding another entire adder. I think this might work. It does work. I still don't fully remember why it works, but I half remember this working, so yay.
I do not remember ever doing this. I probably did, because I've played this game before.
I mean, this is one of those that I think I would have to have an actual whiteboard and draw 4-bit numbers. Yeah. I guess I should have used 4-bit numbers to begin with, like some 4-bit numbers and then add those together and then see if that works. Because if it works with 4 bits, it's going to work with 16. But anything that works with 2 or more bits should probably work with 16. So the way this works is, honestly, essentially intuitive way to explain it. So one thing that is very important is that this actively uses overflow, right? So the carry is lost, and the carry will always be 1. The way this is done.
Yeah.
And so...
By the way, if we do actually want to do that, I do have a whiteboard lying around.
I mean, the thing is, I would probably...
I don't think I want to do it with paint.
I have to actually try to scribble it out. I would have to, think it through, and this is, like you said, you have no control over the board. It would be... I would have to, write some stuff down.
I think I know where you're going with it, so I can probably just draw it on. And you explain it in a process or something.
Sure, go ahead. grab your whiteboard, and then I'll go back to full screen, and then we'll do it.
Problem is, it's a big boy. Is this visible?
I mean, the top part of this
kind of is. Probably all that we need.
I mean,
okay.
It's good that we do this.
The only part that's dubious is me potentially blocking it. I'm gonna just go on to the other side.
I mean, you were like just out of frame, but like I think this way you could write better on the left side of it.
Yeah.
So we want 2 4-bit numbers. It doesn't technically matter which ones they are. We just need to prove that it works. Actually, maybe make the second number smaller
visible.
than the first one. So make it like 0011 for the second number.
Oh.
I'll just write under it, I guess. And
I guess now we just invert that.
Yeah, so it becomes 1100.
Let me get the sponge.
Yeah, okay, we should probably have written them next to each other or something, and then written the actual math under it. But yeah, 1 1 0 0, and then that.
Now we just add them,
which gives us 1 0 0 0.
I think that's.
And then we add 1.
Yes. So this becomes this basically.
Yeah, and then 0, and then 1 in front again.
Yeah.
And now we have to actually figure out what we just did there. So the number up top is 5, and the number below the other number was 3. And when we subtract that, we get 2. Wait. Oh no,
okay,
no.
So yes. Something is wrong with our math.
Yeah, but you are wrong because you forgot to carry the when you added the 2 1s together, you forgot to carry the 1. So it's actually this is on you. So the first digit in front.
Never mind then.
The first digit. No, not there. Up like on the very first step, like after the inversion, the first digit, like the leftmost digit, on the top 2 numbers is 0 and 1, and there's a 1 that carried, so there should be not 1 1 at the bottom, but 1 0. The second digit of the result should be a 0. Because you're...
So, this carries over, so... Oh, right, yes. Yeah. I am dumb.
I mean, it's an oversight, but yeah, this is the number, and so the first 1 is not within the 4 bits, so this would appear in the carry in our model here, which doesn't actually apply, because it just gets lost, basically. And then we actually get the correct output. Cool.
Good stuff.
Actually, let's get to the content. So yeah, this is what it's doing here, right? So you can kind of barely see that this, if I actually use a component, you'll actually be able to see it better, that this carry is in fact outputting a 1, right? This is on. But that gets lost.
It is overflowing.
Yep. So that gets lost. And then we get this result. So that is why that works. I mean, we can't just show that it works in one particular case. With the whiteboard, we didn't entirely show why it works. But I think to do bitwise subtraction is kind of similar to bitwise addition in that case. Because of the overflows. It works, and that's all that matters, really. Equal to 0.
It actually helped me understand it, so it wasn't...
Okay, cool.
For nothing.
Should output 1 if and only if all bits in input are 0. So this is just a 4-bit NOR.
Yeah.
So what we want is to make it a 4-bit OR, but not. So this OR gate. Well, okay, so these. Come on, please. These OR gates. These are the bottom. This one will output 1 exactly if those first two are 1, and this will output 1 if one of this last two is 1 and this input of those first two is 1. And so if any digit is 1, we wire those two together. This will output 1 if any of them are 1, and then we just invert it. Et voila.
Woo! I find it kind of dubious that it doesn't show the truth table anymore on the left side, but
I mean, I feel like it should output 1 if and only if all bits in the input are 0 is relatively simple to explain, but it is fair. Yeah.
As still.
Now there's a component that
it did do that for like a NAND.
If a 16-bit number is negative. Okay, now we need to figure out how exactly they signify negative numbers, first of all. Numbers considered less than 0
so usually
the most significant bit is 1. So
if the highest, that's usually how it's done.
So there's technically 2 ways that this can be interpreted, both of which would yield a negative number. So one is a signed integer, just a regular signed integer, which is to say that the first bit is a sign, and the rest, the 15 bits after, is just a number. But that way is generally not used because it can give you 2 different ways of writing 0, which is 1 and a bunch of zeros, or 0 and a bunch of zeros. So the way that is oftentimes written, which we got explained in college in a very convoluted way that is hard to wrap your head around, but fundamentally what it ends up being is that because the last digit is 2 to the power of 0, then 2 to the power of 1, 2 to the power of 2, so on and so forth, right? As you go like to the front of the number. And the first one normally would be 2 to the 15 if it's like always positive. But if it can be negative, it's sometimes used as 2 to the minus 2 to the 15. Right, so it's just, that is sometimes how it's written. So, as in, if you had all 1s, the number would be minus 1. And then if you have the first one as 1, and then all 1s except for the last one is minus 2. And so, you kind of treat only the first digit as negative, but all the other ones as positive. That is the other way to encode them, which is the one that's actually used.
Yeah.
But either way, the question here is if... this is a splitter. So yeah, this is kind of doesn't make sense, because you don't have splitters on an actual computer, because normally these are already all individual bits.
It's just easier to represent it as one input.
They were asking if the first digit was 1.
These games.
Put 1 to the output, it's done. A select component selects one of 2 inputs for output. Select bit indicates which input is selected if 0, D0 is selected, if 1, D1 is selected. So
this would be very, very easy with the relays.
Oh yeah, because they already do that, right? You just have one that
you could just
one off and one on relay, and then you just put SSD indicator for both of them.
Would be as simple as a NOR gate, NAND gate, as a NAND gate.
What you want here is
it uses the same amount of relays.
You want it to output 1 if D0. So basically, I think what you want is just you want to combine them with an AND gate, and with an AND gate and an inverter, and then you put an OR gate here.
Yes.
And then if this is 0, you want it to output 0, and if it's 1, you output 1. So if this is 1, it should put through 1, and if it is 0, signified here by inverting it, because then it's 1 when it goes in here, then it outputs this.
So yeah, we've basically redone the relays, but just much, much more complicated.
But again, I can't remember ever talking about relays, so I feel like building a NAND out of a relay is almost very backwards, because NANDs are actually on your chips, and they actually build a logic. So I think this is what we're looking for, though. And by the way, you got your wish. We have the table back.
Didn't even notice.
But yeah, so what I've done here is we said it lets through the signal, but of course the way we're handling it here is just to say that if S, the switch, is 1, it connects it with 1. So only if both are 1 does this output 1, and if either one of them is 0, it outputs 0. And this one outputs 1.
Yep.
Exactly when D0 is equal to 1 and S is equal to 0.
So this is basically a multiplexer, what we built here.
Yes. As a matter of fact, I think it's just a multiplexer by another name.
Yep.
This is the simplest possible solution. And then this is a switch which channels data bit through one of
which
two
is a
output channels.
demultiplexer.
It's a demultiplexer, exactly. So select our interval if D is put to C1 or C0. So if S equals 1, we go to 1, right? If S equals 1, we go to 1. And if S equals 0, we go to 0. I mean, it's basically the same logic again, right? If it's
pretty much.
If it's S and D, I'm really bad at connecting those, by the way, if you hadn't noticed. Then it goes to 1.
Yeah.
And if it's not S and D, I don't know how to not make it messy, okay? And it goes to C0. I think this looks fine. There's one intersection.
Good. It's good enough. Yeah. 2. Oh, no, actually, yeah, no, 1. Never mind.
So we done switching. We did demultiplexing and multiplexing. Mission AND is not okay, but it is possible to solve with fewer components. I mean, so wait, 2 components. Because it didn't say fewer NANDs, which would be possible. Would make sense.
Wait.
I think it's about the inverter and the AND. Can we just make the next OR?
No, we can't.
No, that would be stupid. Because if we make it next OR, then it will also output if the switch is 1, but the data is 0. In which case it would output a 1, which we don't want. So we want it to output a 1, because so the one that goes to Z0 is the only one we can simplify. So this Z0 needs to output 1 if not S and D. Not S and D. Which is exactly what we did.
I don't see an easier way to do that, or a way to that uses less components. Is there like a master solution we can look at? Because I'm actually intrigued.
I don't know. So let's see. I don't think there's like a definitive solution that we can just look at. Because we can skip, but I don't think we can I was thinking if there's some way we can get like a component that outputs, but the problem is there are cases where both are 0. Right? So it's not like we can just
Hmm?
Wait. NAND means only if none of them are on. Only if none are on. Which is not what we want.
No, NAND is if all of them are on, then it outputs 0.
Right, so... Wait. If we have a component that can output... Because I'm thinking, right? I think the only way we can possibly simplify this is if we hook into this AND. Right? Which sounds crazy, but kind of makes sense.
Yeah, but I don't see a way to do that. Doesn't make sense.
We would need it to not be AND, but... Oh yeah, no, I think I have it figured out. I'm gonna throw these two away.
Nope, not that button.
So, I think I was onto the right track with the exclusive OR, right? If AND is false, that means the switch is off. But if the data is still on, then this? No, that doesn't work though, because... No, it does work.
Does. Wait.
Because this only outputs... Wait, this only outputs 1 if the switch is at 1. If the switch and data are at 1, this outputs 0, which is what we want. Right? So this definitely checks out. If the switch is on and the input is 0, then both output 0. Then the AND outputs 0 and the D is 0, so that also checks out. If the switch is off...
Oh, yes, I see.
And the data is on, it gets a 0 from the AND, and it gets a 1 from the D. And if both are off, then the AND is off and the D is off. Yep, that is the simplest solution.
That is... Yeah, that makes sense.
This is not the straightforward way of doing it.
Which is good.
This is not...
Yep.
This is not the logically simplest way of doing it. As in, like, just from a human brain to parse this is not the simplest. But I get why this works.
Probably also just component-wise not the simplest one. Or I don't even think it's extendable, so this is, I think, just outright a worse solution.
I mean, yeah.
But it is the lowest in component size, so...
So, which is logically unit. The 2-bit flags... Oh, we're doing opcode now. We're doing opcode.
Which god.
Of the 4 operations are performed on the 2 16-bit inputs X and Y. Okay, so we have AND, OR, XOR, or invert, I assume bitwise for all of them. Because it's really the only way you can do AND. Which we already have the operators for, so we don't need to build those.
That's good.
Bitwise AND, bitwise OR, bitwise XOR, and invert.
It's select 16.
And... Or... What?
I'm surprised we have a select 16, but it does make sense, I guess.
I mean, yeah. So... Oh, right, we need those, actually. Right, these are how we...
Yep.
These are our 4 operations. Invert X. Okay, so this needs to connect to X. All the other operations are A equals X and B equals Y. Those are just the 4 operations. I'm pretty sure we can't get around wiring those up. There might be a way we can wire the AND and the OR together or something, I don't know. But, like, for argument's sake, let's say that we don't want to do anything fancy with those. And then we just need to use these opcodes as a way to run the selector.
Yep.
And we need...
And we'll have to use 3 of those.
Yes. And 2
because we can't have multiple inputs to an output.
Yep, and so...
which is dubious.
So this is basically the setup that we want. I mean, I'm just like layer-wise. So we want to have 2 of these hooked up to this, and then this to decide which of those 2 it is. Meaning that this should be the less significant bit and this the more significant, right? As in, if the right bit gets decided by these, and the left bit gets decided by this. I don't know if that matters. But one bit of the opcode has to be decided by these 2, and one by the other. I'm not even sure if the order matters. I don't think the order does matter, as a matter of fact. So I'm gonna have up0 toggle these 2. Then up1 toggle this.
That makes sense, yep.
So toggle up0. Oh god, we need to invert it here, right? No, wait, we don't. Up.
I would 0. Do the...
No, we don't need to invert it. We do not need to invert it. I got it. This is that then. And now we just need to figure out how to wire those up in a way that we get the right output. Which is to say that if up0 equals 1, we want it to output either XOR or invert. So I need to wire those up to the 1 slots here. Make this 0. So this is this is 1 0. This is 1 1. And then 0 1. So I said this is 1 0. So this also needs to be 0 0, which is this. And this one will be 1 0, which is exclusive or wired up. Wait, I think I did this wrong, didn't I?
Yeah, I think so too.
I wired this one up to the wrong OR. It's to go here. Wait. No.
No.
Let's start from the scratch with the wiring. Okay. I said I wanted to wire these based on opcode 0. So now I need to check that both of these selectors...
just connect the selectors to the higher bit selector.
Okay,
first,
so
I think that might help.
This is opcode 1. So if 1 is 1, I want this. If 1 is 0, I want this. And so this one to have the code 0 1 is this one, which is OR. 0 0 is AND. 1 1 is invert. And 1 0 is XOR.
Yep.
I believe we did it, right?
That should work.
Okay, so by the way, if you were to actually draw this on paper, like, there's way too many intersections here to actually tell what's going on very well. There's better ways to do this.
You can probably just swap the least significant selectors, the places of them, to make it easier to see.
I don't think it gets much better than this, to be honest. I mean, you could have also switched around.
Yeah.
These 2.
That and these 2.
Which tells you that we did it all backwards, basically. But yeah. This is like as close as you're gonna get to this looking somewhat presentable.
And if you want to eliminate even more crossovers, then the high bit select can move that all the way to the left.
Oh yeah, I see. You want to put it like here.
Yeah.
Which actually, now these 2 are crossing again, by the way. So we should have actually not switched those. We should have switched the stuff at the bottom around.
Those will be crossing anyway. Or we will introduce even more crossings through the inputs.
I mean, no, now we just have to switch all of those at the bottom around. Again. But we're not doing that. We're just going to the next level.
Fair enough.
The 2-bit flag opcode determines which of the following 4 arithmetic operations are performed by the 2 60-bit inputs. Okay, so we're just doing the sums before. But now...
Seems like it.
So I have a subtract, we have an add, we have 3 selectors, we have a +1, which is... Do we have an increment here? We do not, so we need this for the increment.
We do not.
And
this is gonna be messy.
Increment. This is a bundler.
Wait, it's the other way around.
Yeah, I'm currently trying to figure out how to unbundle them.
Is there no more elements below?
No, the bundler is the lowest one.
Okay. And really, let's just connect the selectors for now and do the ones we know how to do. Figure out the rest later.
Yeah, but I mean, I'm still saying, like, we need... Oh, wait, we don't need... Yeah, I know, I figured out why that doesn't matter. It does actually not matter. We need an inverter as well, I think. I'll figure it out. So, I think we should actually... Addition, subtraction, x plus y, which actually, those we could actually wire up the other way around, because addition doesn't care about order. Fucking hell.
Yep.
Thank you. And then we need increment, which is uses an adder as well. Increment.
JJ, I think if you want to keep it clean, it would be easier to do that if you wired up the selectors first.
I mean...
So you can arrange them in order.
I know that you're right.
In how you actually...
But I don't care. I need a regular inverter as well. Okay, so I'm currently just trying to construct...
I don't think you need the bundlers.
We need.
Do you?
I need the bundler to make the increment happen. So this is... Actually, the inverter doesn't actually need an input. Because it inputs 1 by default.
Oh, that's good.
So this is 1 as 16-bit, right? And so we add 1 to x. And that is an increment.
Yep.
That is the increment.
You can probably reuse the same increment the invert for the other. Oh, wait, you can probably even reuse the bundler.
Okay.
So you don't even need 2 of them.
Yeah, but how do we... Oh, we just use a subtraction unit, right? We just use a subtraction unit to decrement 1. Yeah. You're right, of course. Subtraction x 1, so we subtract 1. I thought there was going to be like a clever way to subtract 1 by just adding like 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, right? Like just 15 ones and a 0.
Could probably do that too.
I mean, yes, you can. It's just a stupid way of doing it. So now we do the same logic again. 1 and 0. I mean, technically, it makes more sense if we do it this way. And this is going to be the first digit because it's easier for me to navigate. This is going to get a little messy. I'm sorry. It can't really be avoided. I mean, okay, it could be, but it's more effort than it's worth. So, 1. Okay, I shouldn't have done it, but you know what? I'm not going to do it. I'm going to do it the way it's most intuitive for me. I'm sorry if that doesn't make sense, but I always put 1 on the left and 0 on the right. So, because that's how it works. So,
okay.
1 is x minus 1, which is this. 1, 0 is x minus y, which is this. I just realized something. I realized how we could save components.
Oh.
Did you realize that I've wired this into both subtractors?
Yeah.
Which means I can throw this and that away, and then...
Oh, I see. I see.
Wait, this one's already gone. This one's...
Yep.
And then wire this actually... So this one actually goes into subtractor.
God, this is so messy.
It actually is going to get more orderly. So if it starts with opcode 1, it's going to subtract, and if it starts with opcode... So they actually chose the opcodes well. Because if it starts with a 1, it's going to have a subtraction in it. If it starts with a 0, it's going to have an addition. So that is how we're going to select those. And then the second digit tells us if it's a second digit is a 1, then it's going into 1. So,
but we even save on selectors.
Yeah.
Which is good.
Wait, no, it's the same amount of selectors. It's still 3 selectors. We just have one add and subtract fewer. It selects this.
I know, we can't save selectors, right?
And this as...
Because we can reuse the same selector.
Oh, No. We can't... No, we can, right? Because... Yeah, you're right. I'm sorry, you're right. Addition? Subtraction? I'm gonna keep putting the selector over there because we have more space on the canvas on that side.
Yeah.
It does technically mean that there's a crossover here, which is unavoidable. Unless you put it on the left, but there's not enough space on the left.
Happens.
So yeah. Basically what it does is this selects whether we add or subtract, and this selects whether the number we add or subtract is 1 or y. Which, honestly,
yep.
I'm very glad I came up with it, and I'm very glad that you reminded me that I have already done that selection and I don't need another selector. See, that's the thing, right? Like, this is what I was hoping this topic was going to be, right? Because you understand the logic as well as I do, and I'm...
Mm-hmm.
So, if I'm too focused on one solution, then you can come up with another. Right? So once we actually have to think about it, this becomes more cooperative. Because in the beginning, it's trivial, so I could just do it, and because I'm just more assertive, and we actually made a mistake.
You have to actually connect the output.
Oh! I love this. This is like forgetting to put a semicolon at the end of your code in Java or something, and then it just doesn't run.
Yes.
Mm-hmm. This was the stupidest mistake someone could have made. So I think ALU is just an arithmetic logic in it, right? It's just both.
Probably, yeah.
Yep. 0 logic operation.
Yep. Just combines them.
Yeah. So this should be pretty easy. Arithmetic, logic. 0 is logic. U determines which is used. So U... Yep. Okay. And then Y.
I feel ya. Connecting these things is just pain.
And then the opcode should, I guess, be passed through as well. So all of this is kind of trivial what we're doing right now. Oh, I think...
I just see... No. That's different things.
2 or more flags extend operation. When ZX flag is 1, which is the 0 flag, I think, X input is
I don't like
with
this.
0. When SV flag is 1, the X and Y inputs are swapped. No, the opcode still passes through.
That complicates things.
No, the opcode still passes through.
Okay.
The U decides...
We have to do work on the X and Y.
The U decides... So U is a selector.
Mm-hmm.
And if it is 0, we use logic. If it is 1, we use arithmetic. So that part is trivial, actually.
Yep.
Which is what I thought this whole thing was going to be.
These around.
Yeah, I'm in the process of doing that. So this part is trivial, which is why I thought this was going to be a stupid chapter, but then they added the flags, right? So the ZX flag is X is replaced with 0. So actually I do need to disconnect these.
Mm-hmm.
So zx means x is 0, so we select between if zx is 1, x is 0. So if zx is 0, x is x. And if it's 1, then it's nothing. So this is our selector.
Yep.
And then if SW is 1, X and Y are swapped. Which means in another selector that is it's SW for swap, and ZX for 0x. And the outputs...
Mm-hmm.
Oh, why? They're both swap, which is annoying because it outputs... If it's 1, it outputs Y, 0 it outputs X, and then I need 1 that's the other way around. But I can't technically use it instead of X, but I can use this instead of... I think I can use this as our X. I don't know what it's supposed to have when both flags are set. Oh wait. Up 0, 0 is ZX. ZX1 and SW1 will result in the effective operation of minus X. What up 1, 0? Oh, so they're swapped after this, I think. So this flag, I think, comes first, so this actually does have to have actual X in it. And then this one, if I'm understanding it correctly, uses as its X not the actual X, but this X.
Oh, okay.
I think that's how it works. And then this...
It doesn't really add or subtract from the complexity, just changes things around.
This is X. And then we need another one. A selector.
Or Y. Yeah.
For Y. Which is the swap.
I think you need to invert that. Oh no, you don't. You just swap the inputs around. Never mind.
Yeah, so there is... So here I have one connected to Y. So one is connected to X. One is connected to X. Okay, so the reason why this works, because I think I have to explain this one because it is actually a bit out there. Oh no, I forgot. I'd used the actual X again. This should be this X.
Mm-hmm. Yeah.
So the way this works, I mean this is basically X, except that sometimes it's not. It's sometimes 0. That doesn't really matter. And then this one is if the S is equal to 0, it just passes X and Y through. So no, this one, if S is 0, passes Y through. No, it passes X through. Well, this X, but effectively X. And this one, if S is 0, passes Y through. If S is 1, this one passes X through into what is labeled as Y. And this one passes Y through in what is labeled as X. So they swap it around effectively. And, as Sergej taught me, connect the ending.
You connect the output.
Level is not correct.
Wait, which one is not correct?
What is it saying? U0, the woman Z and...
Because I don't...
Oh, right, you don't see it because of my camera. So it says here, if up 0, 1, and U0. So this is the logic operation 0, 1 from the previous chapter. I don't know which one that is, but...
Okay, and
that...
X and Y, W is also 0, right?
And then the ZX and SW are both 1.
Oh, okay.
And they use as an example here, X is equal to 0, and Y is equal to max, and the output is max but should be 0. So I think what might have happened here is that we maybe possibly should have not... we might have gotten this one in the wrong spot, is what I want to say. Which I don't get though, because there's other places, like up here, where it works, right? This has both as 1 as well.
It probably doesn't matter if both inputs are 0.
Oh, because the input is 0, yes. But in this one, y is equal to this. Oh, this is probably an OR. It's probably an AND, right? So it doesn't matter if this is 0 or 1, because this is 0. Yeah, I think I'm gonna suspect, because honestly, this is pretty hard to make reason of, but I suspect that this should actually take its... Whoops.
What the heck
this should take
are
its
you
X
doing?
From here, and these should then thereby take their X, which in this case is this one, from the actual X. This one should take its X from the actual X. And then these should take their X from up here. This looks messier, but I hope this is correct.
Yep.
Yeah, so I just misunderstood the order in which your flags go. Which, honestly, isn't as... Because this is the one bit of text that actually explains which order the flags go in. And it's not intuitive. Like, at all. I'm sorry. It's just not.
It really is not.
And conditions. I think this might be the last one because we have been going for a while now.
Have we? What time is it?
It's like 11.
Oh, we definitely have. Yes.
The three flags indicate three possible conditions for the number X. LT is less than 0. For LT is less than, EQ is equal to, and GT is greater than 0. I was
actually going into branches. After this, we're Turing complete.
Oh, cool. I mean, aren't we just Turing complete by having NANDs?
We don't actually have any component to do branching for us.
I mean, we built all of this out of NANDs anyways, right? So...
I mean, yes. But just by having NANDs, you aren't automatically Turing complete.
Okay.
You can build something Turing complete out of NANDs, but...
Yeah, so by having an infinite amount of NANDs, you should be Turing complete.
If you wire them up correctly, yeah.
Yes. Okay, cool. So 000 should never happen, nor should... Oh, fuck! Okay.
Actually, never mind. We already were Turing complete. We did have decisions in the ALU. Never mind. I'm dumb.
So, the flags can be combined. So, it can never be all 0 or all 1. But, if it can express less than, equals, greater than, greater or equal, and less or equal. Or not equal. Okay.
What is the...
Yeah, I'm a bit confused. Let's see, what was level
What do we need to do?
There. No, there's a...
No, that's it.
So if we go to...
Can you maybe hide the camera? My camera? Because I don't actually see the whole...
Oh, let's see. This is kind of tricky because...
That might hide some crucial information.
I think it's this one. Yep, there we go.
Yes.
Because the thing is, I have to look at my second screen, which is far away, and try to figure out which exact source to disable, so as to not accidentally disable the wrong thing. But this is complicated because I don't get what they...
Okay, I see. I see, yes.
Okay. I accidentally briefly disabled your audio. I hope that doesn't affect anything.
I
did re-enable
hopefully
it, and
not.
It does still track it. It should be fine.
Okay, that's good.
If the flag for the is 1, then the output is 1.
Yep. If if x is actually 0 and you pass in the equals flag, then you output 1. if x is 0 and you pass in any other flag, like lower or greater, you output 0.
Yeah,
because
no,
it doesn't
I understand
match.
what they want. Yeah, they want to know if the flags are correct, basically.
Okay.
But specifically, if there are multiple flags, they do have a specific meaning as well.
Oh, they do?
I mean, yes, that's what the table said, which is what I thought I was showing you.
I didn't pay close enough attention and didn't remember.
Okay, so if 2 are set as 1, if
I
equals
see.
and greater is, then it's if it's greater or equals.
I see.
And
Yep.
And so basically they're just all or connections, which is.
But that logic is just pretty easy because we just or everything.
Yeah. So we have
3 ands.
Is negative, is 0, and we don't have an x positive, so we need an inverter for 16-bit, which we don't have.
We don't need 16-bit.
Oh, right, because the output is just 1-bit, yeah. So, this is not
one
negative,
thing, though,
which actually is a problem, because that is also equal to 0, then.
That includes 0. Yep.
So, not 0 and not negative, right? That's what we want?
Yep.
So, greater than 0 is actually NAND. Wait, no, that's not it. It's neither of
that's
those.
a NOR we need.
NOR.
We need a NOR.
Well, we never actually built a NOR, which is kind of disappointing. Not because it would have been very difficult to build, but just because now we have to use 2 gates to make this happen.
Yeah.
But yeah, so we have less than, equal, and then greater than. This is the best way I can display it next to each other.
Yeah.
So, both of these just wire into the number. Which means I've got to put them here.
Yeah, I think that's better.
Okay. And then we have the 3 actual conditions. And should output 1 if the flags...
That would just be 3 ands and 3 ors to then combine them together.
Well, except that there can be multiple flags true at once. Right, so...
I mean, yeah. That's why we need the ors.
Because it's or connected, so... Right, so what you're saying is, it doesn't matter if...
I would put A to the flags, because that less crossovers, but yeah.
That is very reasonable. So what you're saying is it doesn't... No, this is the wrong one, obviously.
No. Yeah.
So I'm saying it's like this, and then as long as at least one of the conditions is met... Oh wait, no. There's one thing that that we're not getting if we OR these all up, though. And that is...
Which is?
It can never... Oh no, wait, no, it says output 1 when 1 will 1 always. Right, so actually it does check out. Never mind. I thought it said never. Because then we would have had to make special logic just for if it's 1, 1, 1. But no, they actually
because
that.
X is always going to be up to 0 or more.
Yes. I also kind of low-key wish we had ANDs and ORs with more inputs. Because ORs with 3 inputs would totally be possible, which would just be... Wait, we don't actually need 3 ORs. You said 3 ORs. We only need 2.
Yeah, I'm done. Never mind that.
Yep.
This works.
I mean, if we had 4, we would have needed... Yeah.
Yeah.
I think this is already correct. I don't think this is actually that complicated. Yeah.
Mm-hmm.
And we are done with everything in ALUs. So, we're not going to do latches today, which means we're not going to do anything timed today, because latches and flip-flops is I think, when we get into timing, and then counters and stuff. Oh, yeah. So, so we might actually finish this at some point, in which case I'll off-screen do the NANDs and everything back to where we had them. so that
Yeah.
it can actually count them properly. Because I think this saves it in cookies.
Hopefully.
So that brings us to our songs of the week.
Right. I do have songs of the week. Let me just pull that up real quick. So my song of the week is Comedy by Gen Hoshino. Hoshino, sorry.
争い合って壊れかかったこのお茶目な星で生まれ落ちた日からよそ者涙枯れ果てた帰りゆく場所は夢
Honestly, I'm not a big fan, but
Really?
I mean, like, it's hard to like definitively say like after having listened to like 20 seconds of the song once.
I mean, yeah.
But like intuitively, I want to say not a big fan.
Fair enough. But the style is carried throughout the song, so
Yeah, I'm
you
not.
probably
getting
have a good
25.
idea of the song. Okay.
Anything else you wanted to add about that particular song?
Not really.
Which brings us to my song of the week, which is Arms of Salvation by The Common Linnets.
Just hold on to the knowing that it's gonna be alright. And the arms of salvation will be holding you tonight. Yes, they will.
Yeah, it's a song.
Yeah.
I mean, I've also,
That's the kind of song we listen to when we go camping.
yeah. I mean, probably not even that, because I don't think we actually had any songs of that band, because I don't think Alex necessarily knew of them at the time. But yeah.
But it's the kind of song.
Yeah, no, it's country, right? Like that's what it is.
Mhm.
Yeah, so this is of course a country song from the I think Dutch band The Common Linnets. We have, well, I can't say I have, but like our household has both of their albums. I don't think they've brought a third one by now, and they're both overall pretty good. So
Yeah.
The Common Linnets. Let's see. Wikipedia says, yep, they have 2 albums. And hey, would you look at that? They both peaked at 1 in the Netherlands. Who would have thought? They all did relatively well in the German charts as well, which is why I know of them. And I don't see any US, so might actually be something new to our biggest demographic here. And you know what? I'm looking up things on Wikipedia, and this is a special episode. Do you want me to look up the one thing on Wikipedia that I always look up on Wikipedia? This could be very devastating.
Yes.
Let's see, oldest people. Currently oldest. Oh.
Did it change?
10 oldest certified people ever. That's what I'm looking for. 10 oldest living people. Yeah. So it changed. Which, that's pretty good. So let's see. Let's look at the exact date. So Kana Tanaka became the second oldest person ever a while back, beating out third place Sarah Knaus by 10 days. So she managed to live just about long enough to outpace that. And she died on the 19th of April, 2022. So that's a thing. And that makes the currently oldest living person in the world, Lucille Rondon, who used to be the second oldest living person for honestly quite a while as well. She was also the oldest person to be verified to have survived the coronavirus, because she got it and then she recovered. She's currently
impressive.
18 days and 118 years and 97 days, that way around, old, which makes her exactly 1 year younger than the current third place person, and she's fourth place of all time. So she has to live another year to tie for third, and then, another 10 days on top of that to get to second, and then, another, 3.5 years. No, not quite. 3 years and 2 months to get to first. Because, Jean Calment, who is in first place of the all-time list, lived for over 3 years longer than the person second place.
That is just such a ridiculous long time.
122 years,
it's crazy.
164 days. So yeah, the current oldest living person and the oldest living person ever are both from France. So that is us checking in on oldest living people, which normally doesn't change when we look at it, which is weird. So it's actually not that weird that it changed.
Mm-hmm.
I think that is actually it for today, though. If you enjoyed this video, like, comment, subscribe, all that good stuff. This is probably going to get less views than the previous podcast, but it's fine. I should have said fewer. I'm usually the person that complains when people say listen rather than fewer. It's probably going to get fewer views because they're countable, right? It's not a mass number.
Yes.
Than the previous video, which actually popped off. Like, comment, subscribe. I said that. Join the Discord server, links in the description below. And Sergej.
That's it.
That's it.